Welcome everyone, thanks for joining us. We will be talking about gRPC Protobuf at Uber. I am Shuyi, engineering manager at Uber, leading open source adoption, development, and innovation in open source. Together, we have Karen here. Karen is a senior engineer on search platform team, focusing on building and scaling the search platform, and has been pioneer gRPC Proto adoption at Uber. Here's agenda for today. We will talk about innovation, like motivation, and then we will deep dive on the architecture and how it works, and the performance impact at the scale, and we will cover a real-world use case at Uber. Then we'll talk about lastly we'll talk about share about the current state and the roadmap. So why we want the gRPC and Protobuf? Before that, maybe let's talk about what is gRPC and Protobuf. The gRPC is an open source remote procedure call framework created by Google, and in most of cases is use Protobuf. And a Protobuf is a compact, language-neutral data serialization format, which is used to define service contract and to structure the data. So the gRPC core supports different transport protocols. HTTP2 is the most commonly used ones. In HTTP2, communication between client and server happens through the single TCP connection. And within the connection, there can be multiple bidirectional flows of bytes, which are called streams. As shown in the top diagram, the message passed between the client and server breaks down into multiple frames. It allowed multiple messages to be multiplexed in a single connection, which compared to the HTTP, as we know, which only have one request per TCP connection per at a time. There are multiple communication patterns in gRPC. There's a unary, server streaming, client streaming, bidirectional streaming, etc. And then today, what we're implementing in open source is a unary one. As shown in the second below diagram, in unary RPC, the client triggers communication, which consists of request header, and a binary message, and followed by the end of stream flag to notify the server that the client finished sending the content. In response, the similar is followed by the trailer. So we just talked about what is gRPC and Protobuf in high level, and the real question is why we should adopt. So at the rest of the entire session, Karen will cover most of why and the technical details. But here I just very briefly talk about in Uber stack. The wins show up in three categories. So first, the gRPC Proto is a very industry standard which widely used protocol and format, and is heavily adopted and used at Uber. Secondly, we observe performance gain and efficiency in data transmission. Last one is it enables the opportunity to more streaming support. For example, in the further integration with Aeroflight, streaming in transport layer can achieve real end-to-end. By here, we will deep dive more later session. We have another talk about the Aero, which in the conference later today, maybe tomorrow. So next, I'd like to give a high-level overview of Uber search at Uber. As of today, majority of Uber use case run on gRPC Proto for our in-house search platform called SIA and Lucene Plus, supporting very critical large-scale business use case, including Uber Eats, Maps, and more. We also have many OpenSearch/Elasticsearch use case, including M3, which is powering the entire Uber metrics monitoring use cases, and Bliss, which is partially powered help.uber.exe if you ever get a chance to cut the ticket or whatever. That's the service that's supporting that. The gRPC protocol ecosystem at Uber is very mature, and it with all different advanced IDL management and client-generated support. So I'm happy to announce, starting the OpenSearch release to 3.2, the gRPC bulk and key inquiry are generally available. It provides alternative to gRPC, the HTTP JSON with gRPC client server communication using Protobuf for lower overhead and fast serialization. To enable the gRPC API, it requires to add the specific settings in the OpenSearch YAML file, which is as shown in the right corner of the slide. Here's a kind of general example of the request look like. I will hand over to Karen to deep dive on the technical details. Yeah.
Thanks, Shuyi. So next I'll be talking a bit more about how the gRPC transport works behind the hood. So to start with the architecture diagram, so the gRPC transport runs in parallel to the HTTP one. The entry point to this diagram is on the right side, where the client starts with either constructing a gRPC or an HTTP client. Should they be constructing a gRPC client, they'd be sending Protobuf requests, and should it be an HTTP client, it'd be a JSON request. Once that request gets constructed on the client side, it'll get sent over to the OpenSearch server, the transport layer on this diagram. The gRPC server and the HTTP server run on a different set of port ranges, respectively, which is how we're able to support both transports in parallel. Next, that request, whether it's JSON or Protobuf, gets forwarded over to the respective service handlers, whether that's the gRPC one or the HTTP one. And later that gets forwarded over to the the data format conversion layer. So on the gRPC side, we have a set of utility methods called Protobuf utilities that will be converting the Protobuf request into an internal search request POJO. Vice versa, on the JSON side, we'll have something converting the JSON, which you might be familiar with the from X content methods. That'll be converting the JSON into the search request POJO as well. So once it reaches that search request POJO layer, the rest of the path is the same for both gRPC and HTTP. It'll send it over to the coordinator node, execute it on all the shards, return the search request, and once that the search response, and once that search response POJO is returned, that again gets converted back into a proto or POJO and a proto or JSON and gets returned back to the client. At the top of the diagram, you might see there's an SPI extension layer for the gRPC path. What that enables us to do is for external plugins like the KNN plugin to implement their own query proto converters, which will allow them to also leverage the gRPC transport. So an example that we have implemented so far is the KNN external plugin, which is able to convert their own protos into search requests to send back to the gRPC server and have them fulfilled. So now you may be wondering, with the new transport and the new data format that we're using, which is Protobuf, where do these Protobufs actually come from? So I wanted to detail a bit more into the Protobuf conversion process that is based off of the Open API spec today, OpenSearch API spec. So the OpenSearch API spec today serves as the source of truth for all REST APIs, and by introducing this new transport, we still aim to keep the gRPC and HTTP APIs consistent, and thus we wanted the source of truth to remain the OpenSearch spec. As such, we had a problem to solve, and we needed a way to consistently, scalably, and error-free way to convert this Open API spec into Protobufs. But currently, there doesn't exist any tooling available in order to do that, and having a human to manually do them is just, it's not consistent and it's not scalable either. So what we ended up doing is we leveraged an existing tool out there, Open API Generator, which is able to convert Open API specs into a variety of different formats, Protobuf included. But currently the Protobuf support within this tool is not super mature. So what we had to end up doing was continue to contribute features and more. So this is also an open source project, so we ended up contributing more features to support the Open API to Protobuf conversion within this tool. Yet that also still wasn't enough. So after having somewhat of a maturity in this tool, there were still some ambiguities in the spec that we had to address. For example, OpenSearch APIs support an underscore source field, and sometimes in the same API it also supports a source field. But fields that are preceded with leading underscores are not supported field names in Protobuf. So what the conversion tool would do is it would convert it into a field called source1 and source2, and that's not ideal. So what we had to do is we added, so to address this problem specifically, we added a pre-processing step before feeding the Open API spec into the generator to convert to protobufs. What we did is we would rename these fields from underscore source to something else in order to address the duplication problem and have all the namings be more ergonomic. In addition to the pre-processing step, we also had a post-processing step after those protobufs were generated. In order to maintain backward compatibility of protobufs, the field numbers must remain the same. But say a new field in the spec was added, that would kind of push back all the numberings of later fields in the protobuf, and that would pretty much break the backward compatibility of all protobufs. So in the post-processing step, we would renumber those protobuf fields to keep the same numbers as the previous version of protobufs, and then add that new field at the end to preserve backward compatibility. So there are a whole lot more rules with this protobuf conversion step, and those are outlined in more detail in the spec issue linked below, which is OpenSearch API spec issue 677, I believe. And the current state of the world today is that we have this tooling and automation mostly completed and residing in the OpenSearch Protobufs repo, as well as the raw proto files that are generated from these, and some tooling in there to further convert those protobufs into generated language libraries like Java, Python, and Go. So just to share a brief example of what a spec to proto conversion would look like. On the left is an example of an Open API spec for the underscore search endpoint that we're all familiar with. And on the right is an example of the generated protobuf. So this is obviously an oversimplified example of the search API with many fields removed. But just to illustrate the high-level idea, the search underscore search endpoint would get converted into a corresponding gRPC search endpoint, which takes in a search request and returns a search response. Some key differences in HTTP are that in HTTP there are verbs like get, put, post, delete, which are not present in gRPC, but the expected payload for all of those the different verbs are the same. So in the protobuf conversion, we would opt to convert only one of the payloads of these, for example, get, and we would ignore the post. Furthermore, HTTP has URL parameters and a request body, a differentiation which is also not present in gRPC. So for this, we would combine the request body and the URL parameters into one protobuf message. And finally, HTTP responses go from 200, 4xx, 5xx, et cetera. For gRPC, the difference is that non-status OK error messages do not actually return a protobuf schema. It simply terminates the RPC and adds some metadata in the error. So none of the HTTP error status codes needed to be converted to protobufs because the gRPC side would never reach that point. Again, for more info, there is a spec issue open, 677, with a more detailed conversion rules doc linked in there. So next I wanted to talk about briefly how these protobufs are distributed and how they can be used by clients and servers alike. Starting from the left to the right of the diagram, the API spec is, as we just talked about, converted to protobufs. Those protobufs, there exists some tooling in the repo right now which is able to convert, to compile those protobufs using Proto-C and Bazel in order to create the generated language libraries for Java, Python, and Go. Those currently are published, some of them are currently published so for Java, we're publishing them to Maven Central. For Python, we're publishing them to PyPy. And they're also available as GitHub release artifacts for clients to download so that they can generate their own libraries as well for the language that they're using, C++, Rust, be what it might be. And then on the server side, OpenSearch Core, which is where the gRPC server resides, is written in Java. So it's going to be downloading the protobufs from Maven Central, importing it into Core, and then providing it as a dependency at runtime to external plugins as well. Let's see. So now that we've gone through like a high level of how it works, just to summarize some of the key differences between the HTTP and gRPC protocols. First is enablement. So the HTTP layer, obviously it's the default enabled protocol today. For gRPC, although it's installed by default in OpenSearch 3.2 and beyond distributions, it still needs to be enabled manually by adding a setting in the OpenSearch.yaml config. And this runs in parallel to the HTTP endpoints on a different set of ports. In terms of network configurations, because of the differences between HTTP and gRPC, there are some differences in the configurations that users can specify. I won't go too much into detail about these, but some examples include the max header size for HTTP or the max response size for gRPC, and more details about these can be found on the documentation website. In terms of service endpoints and schemas, as mentioned in the previous spec section, HTTP has a set of verbs, URL params, request parameters, none of which are present in gRPC, and gRPC is able to support streaming, as Shuyi previously mentioned. So that is another opportunity that we plan to capitalize on in the future. Lastly, in terms of error handling, HTTP returns a JSON payload for all types of error codes, whether that's successful or unsuccessful, but gRPC only returns a protobuf response for successful ones, followed by a kind of metadata, like a trailer metadata for any of the error codes that it returns. So next, I'd like to talk about the performance impact of using gRPC over HTTP, whether it's through our benchmarking or through real-world production use cases that we were able to onboard at Uber. In this section of the talk, I'll be breaking it down into 3 parts. First, we'll talk about the bulk API. Second, the KNN search API. And third, our benchmarking with search and ingestion while using Smile. So starting with bulk, gRPC compared to HTTP was able to exhibit uncontestably better performance. For this particular benchmark, which we benchmark across payload sizes of 0.5 to 4 megabytes, 4 megabytes being the gRPC default limit, we were able to see a 15 to 40% improvement across all these payloads, and this shows P99.9, but across P50 and P90, we saw a similar improvement as well. Bulk is also more unique. It's different than search in the way that the request sizes for bulk are usually larger than the response sizes because the documents that we're aiming to ingest are on the request side. And what we found from our server flame graphs was that gRPC is especially efficient when it comes to larger requests, which is why the bulk API was able to exhibit such huge gains. Now, to apply that to the real world, what we were able to find in our production M3 indexer at Uber was that these latency gains similarly translated to production. There were no issues over the network. In fact, sometimes it performed even better. And at the P50 levels, we saw a 20% improvement in the M3 indexer latency reduction, and at the P99 levels, we saw a 10% improvement. To give a bit of a better picture on the scale of the M3 indexer, M3 is the Uber's in-house metrics platform, and it's responsible for storing and querying the metrics from all of Uber's services. And this M3 indexer is the ingestion service that ingests the metrics into the M3 into the metrics database. For this particular screenshot, the QPS was roughly 5.5 thousand, which we have also seen higher than that in production. Another real-world example at Uber were the throughput gains that we saw on the batch ingestion jobs for OpenSearch customers. So these batch ingestion jobs are essentially a Spark job that different customers can run with different configurations in order to ingest their data from Hive or whatever into OpenSearch. To highlight 3 of the use cases that we benchmarked and migrated over to gRPC, No Free Trip, MP13N, and uWork all saw extremely good improvements while running on gRPC instead of HTTP. So No Free Trip is an important use case that helps to detect fraud detection for riders at Uber. MP13N, which is short for marketing personalization, is used to make personalized and tailored recommendations for users like restaurants, offers, etc. And finally, uWork is an important internal tool that's used as a unified console to author and manage a variety of batch and streaming data workflows. So across all 3 of these use cases, we saw anywhere from a 20 to 30% latency throughput gain, as in a reduction in the time it took for the Spark job to complete. And as such, gRPC today is the default protocol for running all of OpenSearch batch ingestion jobs at Uber. So here's just an example of a Spark job that was run for a particular use case, No Free Trip. The HTTP job, as you can see, took almost 3 hours to run, while the gRPC side ran in under just 2 hours. So that's around a 30% reduction in the Spark job runtime. So now that we've talked about bulk, the next topic that we wanted to talk about was the search performance, specifically KNN search. So for KNN search, similar to bulk, we observed quite significant latency benefits. KNN search is, we just had a KNN talk, so you're probably familiar already. But on the query side, there is a vector provided that can be a varying dimension size, anywhere from a few hundred to maybe I think the limit is 1,000 or 10,000, but KNN maintainers, feel free to correct me on that. So we benchmarked the KNN query across different dimension sizes, and what we saw was that the larger the number of dimensions, as in the larger the request size, the better the gains of gRPC were over HTTP. So on the graph on the left, we see that the latency gains of a query with 256 dimensions was roughly, this text is too small for me to see, but I think it was around 20 to 30, 81%. And meanwhile, the improvement for a higher dimension use case, 1572, was around 89%. Furthermore, we observed that not only does the latency get benefited from gRPC, but also the payload size gets reduced. So the greater the request size, the more the reduction we saw in payload for gRPC, as shown on the graph on the right. So applying this back to the real world, one of the use cases that we migrated at Uber was Bliss Search. As Shuyi mentioned previously, Bliss Search is a service that powers the backend help.uber.com. This service is where people would file support tickets for eats, drives, and other cases as well. This was a particularly high dimension use case with 1536 dimensions. And in production, what we observed at P50 was that the Bliss Search REST latency took a mere 1/2 of, or the gRPC latency was only a half of what it was at REST. And at the P99 and P99.9 levels, an even higher gain of requiring only a third of the HTTP latency. So overall, we saw a 50 to 70% end-to-end latency reduction using gRPC. Another KNN use case, which was slightly lower dimension, was No Free Trip. This one had 256 dimensions instead of 1572. And for this use case, we saw a modest yet still observable and significant performance gain of 5 to 12%. This use case was covered also in the batch ingestion slide, but this use case detects fraud detection for riders. And yeah, on screen is shown the end-to-end latency for this use case post-migration between HTTP and gRPC. So now that we've covered the good parts of bulk and KNN and also explored some of the use cases that were migrated at Uber, we wanted to do a deep dive on some of the learnings that we had through benchmarking and how we think it might be more accurate to measure gRPC versus HTTP protocol performance. So in this specific test, which was for a KNN query, what we observed is that on the server side, the HTTP protocol performed similarly compared to the gRPC one. Yet when we tested this end-to-end, the gRPC performance was significantly better than HTTP. So we were wondering what caused this discrepancy. So we did some investigation, collected some flame graphs, instrumented some metrics, did some more research. And what we realized is that measuring pure server-side performance for a protocol may not always be fully sufficient. It may not be telling the full picture. So there are 3 layers of performance as shown on this diagram. We have the server layer, the network layer, and the client side. So on the server side, which is what we previously showed in previous benchmarks, gRPC generally performs much better on the request side and potentially the same or maybe slightly worse on the response side. However, across the network layer, gRPC performed uncontestably better than HTTP due to the efficiency of the protocol as well as the reduction in payload size that was delivered from using Protobuf as a binary format instead of JSON as a textual format. And finally, on the client side, we saw that gRPC was usually faster to decode or parse on the client side due to Protobuf being structured data already, as compared to JSON, which was harder to parse on the client side and thus took longer latency. So across all 3 layers, gRPC performed significantly better, besides on the component of the server-side response conversion in certain cases. So we wanted to investigate what we could do to improve the single aspect where gRPC was underperforming compared to HTTP. So we dove deep into the server response performance, and these were the 2 root causes that we found were responsible for this performance difference. So first is the way that X content is implemented within OpenSearch. In HTTP, specifically when using JSON as the X content format, the X content builder is able to generate and serialize the JSON on the fly. As in, it doesn't need to first load the entire JSON into a DOM-style tree, generate the whole response, and then stringify it. It is able to append the curly brace, append the quote, append the text directly, which is kind of doing the construction and serialization all in one step. Meanwhile, on the gRPC proto side, what it had to do was take the entire response, create a protobuf builder for it, and then serialize it. So this was causing some marginal server-side difference between gRPC and HTTP, specifically when we tested using a match-all source-false document, source-false query, which returns no documents. But in the same benchmark, we also measured the end-to-end latency, and gRPC still won on the match-all source-false end-to-end latency. So the second reason we wanted to touch upon was the performance when there were documents in the response. So Protobuf today is currently taking a JSON document and just returning it as bytes in the Protobuf response, which means that it's not really capitalizing fully on the benefits of Protobuf. So in that aspect, when large documents are returned in the response, then HTTP generally performs better from a purely server-side measurement. However, we aim to find a workaround for this problem, and we were able to find one by finding a different document encoding format that was more efficient and was able to flip the tables and make gRPC the better performing protocol. So I'll talk about that on the next slide. So here, instead of JSON, we attempted to encode a document as a SMILE format instead. And SMILE, for those of you who aren't familiar with it, is a binary representation of the generic JSON data model. So with SMILE, this flipped the performance latency between gRPC and HTTP completely. gRPC SMILE across all the 4 different things that we benchmark, which was gRPC SMILE, gRPC JSON, HTTP JSON, HTTP SMILE, came out on top as the fastest out of all 4. So gRPC Smile was 30% faster than HTTP JSON, 45% faster than gRPC JSON, and 47% faster than HTTP Smile. Now you might be thinking, so is the reason that gRPC is performing better because Smile is good or because gRPC is good? So here we can see that the HTTP Smile performance actually underperformed the HTTP JSON performance. So no, the gains are not from just simply having Smile. So to explain further why the HTTP JSON performance was better than the HTTP Smile one, despite Smile being a smaller and more compressed format, it's because of the way that the JSON and Smile X content builders are implemented inside of OpenSearch. So with JSON, HTTP is able to efficiently write the JSON as raw writes and, as previously mentioned, do the construction and serialization all in one step. However, with Smile, that is not done. Raw writes are disabled for that X content implementation. So HTTP would have to fall back on creating the entire Smile response and then serializing all at the end, which was causing HTTP Smile to underperform HTTP JSON. So previously, purely on the server side, we saw that gRPC Smile performed extremely well compared to all the other protocols and data formats. And we wanted to further investigate whether the end-to-end latency would still be okay while using gRPC Smile, because we assumed that Smile would be harder to parse on the client side than JSON was. However, that was proven to be untrue. So in Java, we used the faster XML Jackson library to decode Smile and compared that to parsing the same JSON payload. And we saw that Smile had a 20 to 40% faster response decoding and parsing time than the JSON payload. And furthermore, across the network, the gRPC Smile was able to be sent much faster across the network than compared to other ones, mostly due to a payload size reduction of being around 40 to 50% smaller than its JSON counterparts. So overall, with search, we saw that gRPC Smile outperformed any of the alternative protocols and data formats at both the server layer, the client side, as well as across the network layer. With that, we were thinking, okay, why not benchmark the ingestion endpoint with Smile as well? The ingestion endpoint was already doing well with JSON, but there's always improvements. There's always something better that we can do. So even with ingestion, we were able to see the same kind of gain. We did two different benchmarks, one with 30,000 docs and one with 10,000 docs. And in both, we observed a sizable ingestion latency decrease of around 30 to 40%. Furthermore, if you tiny font, but if you take a closer look at the gray diagrams at the top, you can see that even the index size reduced when ingesting with Smile instead of with JSON by around 30 to 35%, which can help to save on disk usage within the cluster. So that was a lot to cover in the performance section, but some key takeaways that I wanted to ensure that some key takeaways of this part is that overall, gRPC is a efficient and very good protocol in terms of performance. Generally, it performs better than HTTP, or at least as good. However, performance is workload dependent, and it is more nuanced than just simply benchmarking the server-side performance. It would be better described as the sum of the gains across three different components, which is the server side, the network layer, as well as the client side. So on the server side, gRPC is definitively better for requests, such as large bulk requests or KNN queries with large numbers of dimensions. And on the response side, Smile definitely helps with the response, while JSON with gRPC is less efficient. On the network layer, Protobuf being a binary payload, a binary format, has a smaller payload, and gRPC using HTTP2 generally results in faster transmission across the network. And finally, on the client side, Protobuf is faster to parse than JSON in most cases. So across the end-to-end stack, gRPC generally performs better than HTTP, and in order to capitalize on the greatest gains that gRPC can provide, having request-heavy workloads as well as SMILE documents would be the way to go. With that, I'll hand that over to Shuyi.
Time check. Okay, so I will quickly go through the next. Right now, currently we have select gRPC API generally available, as mentioned earlier, including bulk and kin without filter. At Uber, we have much more query types supported for the production, but we will contribute upstream all the changes in the coming releases, so stay tuned. The generated protobufs available for select language, including Java, Python, Go, as well as like raw proto files for other languages. Plus, there's secure support as well. Current ongoing effort, including the OSB OpenSearch benchmark support, which we collaborate with AWS team, and also there's ongoing like specs fix and full automation for the protobuf conversion, and there will be more query type upstream and API support. Okay, so this is high level about like the roadmaps. Looks like last year we have 2 minutes. Maybe I would just skip. But our goal by end of year is have the majority of the we prioritize Uber use case, but majority of the query type supported in the open source. And at Uber we will be generally available for all the Uber use cases. Next, here's the documentation for how adopt and onboard to the gRPC in 3.2, and we will have more in the next release. We'd like to welcome everyone to have more engagement and contributing from the community to make the feature better. So yeah, here's how we can you can contribute to the gRPC and the protobuf feature. So now we have around 2 minutes, and we can open to any question. Thank you. That's all for the talks. Any questions? No? Okay. Do you want to answer that?
The language clients, right? Yeah.
So on the client side, if I have a source, I can issue data like opportunities, or reads to OpenSearch. These are done with JSON, right? Against API. So is there a general or efficient gRPC or
So for now, we only offer, at this moment, we only offer the generated protos and for the select language, and you can integrate with that. But ideally, that's what we're looking for in the next step is the client support. So right now we have OpenSearch Java, OpenSearch Go, et cetera, the high-level language client. So we plan to integrate with that with the gRPC. So it will be more engagement from clients that are easy to integrate with the gRPC. That's our plan. But right now, I have to work around with like generated protos. Yeah. Sorry, the SMILE one. The SMILE one, right?
Yeah.
Yeah.
Yeah. So this was a KNN data set that we ingested. On the left side benchmark with 30K documents at 256 dimensions, we saw index size of JSON was 100 megabytes versus the index size of SMILE was 70 megabytes, with a different benchmark of 10K docs and 256 dimensions. It looks like the JSON index is 63 megabytes and the SMILE one is 42 megabytes. So across both, we saw a consistent reduction in index size. Yeah. Right, yeah.
Okay, cool. Oh, we have one more.
It didn't have to be very large, I think. So for bulk, at 0.5 megabytes, we're already seeing gains of gRPC. For KNN, at 256 dimensions, we didn't, which is, I remember that was only around like 12 kilobytes of a request, or it wasn't even 12, it was like 1 kilobyte request size. We didn't see much of a difference. But at 512, which I think is 12 kilobytes, we already began to see an improvement with gRPC. Yeah. Sorry.
So you mean the resource consumption, right? Do we see the benefits? That's a good question. So right now, since we haven't reached, like all the use case we onboard is a relative small use case. And then we don't have a good example of showcase in the production about the CPU, all the like consumption is very similar. We don't see a dramatic drops or improved or in that way. But with more and more use case onboarding, we will collect the data and see if we see the CPU or other consumption gain there. So right now we don't have good data point. Yeah, that's a part. We did a bulk. There's one of the, I think AWS folks working on that. So the bulk has already have some OSB numbers, which very similar, 30%-ish improvement of the latency and throughput. And for there are big 5 data set. I remember on the server latency is similar actually. So, and we didn't measure the end-to-end at that point. So that's the ongoing effort. We will publish more of the OSB standard data set in the coming blog and then, yeah. Okay, thank you guys.
Thank you.